In this video, we look at congruence, and we start with modular systems. And I'm choosing as an example modulo 13. Okay, so we have a modular system. The modulus divides into any number, and we look at the remainder when that modulus divides into any number. So in this example, we have 25. We divide 13 into 25. We have a remainder of 12. So 12 is one of the 12 what we call residue classes, or remainders from all numbers being divided by the modulus. And it's true that if we say, and the way this is written, we read it, 25 is congruent to 12 modulo 13. That's also true that 12 is congruent with 25 modulo 13. So those two values are reflexive. Also, if it's true that 25 is congruent with 12 modulo 13, we can also say that 25 is congruent with -1 modulo 13. -1 meaning that 12 is 1 less than 13. That's a remainder of 1 less than 13. So that's how that works. All numbers are congruent for a given modulus if they yield the same remainder when being divided by that modulus. Okay, and so what is the usefulness of this? Well, let's take a look at, say someone were to say, or to ask, what day of the week would it be 200 days from today? Now you can divide 200 by 7, and you would get a remainder 4, and say, well, just add 4 to the present day, and that'll be the day of the week. 4 to the present day of the week, and what you'd get would be the day of the week 200 days from now. Or you could look at it and say, well, we know 203 is a multiple of 7, and so over 203 it would be the same day of the week. But since it's 200, 3 less than 203, then the day of the week would be 3 days before the present day of the week. See how that works? So in representing modular systems, so the modular system is a system based on a given modulus. In this example, we chose a modulus of 13. We symbolically represent the 13, modular system is 13 as Z subscript 13. And next to this, we have the residue classes for 13, 1 through 12. So you can get all that in there, 1 through 12. Okay, now we could list the remainders or residue systems as 1 through 12. That's all values are positive. Or we could say the first 6 are 6, and then for 7, right, that corresponds to -6, because if we take 6 away from 13, we have 7. Take 5 away, we get 8. Take 4 away, we get 9. Take 3 away, we get 10, and so on. And in modular systems, each number, each residue class has an inverse, always has an inverse if the modulus is a prime number. In this case, 13 is a prime number, so yes, every number has its inverse. That is not true in the case of a modulus that is a composite number, not a prime, but composite. The reason for that is for every number in the residue class that happens to be a factor of the modulus, there's no way to get an inverse. By inverse, I mean a number multiplied by that number that would yield 1 in the modulus. But since we do have a prime number modulus, I've listed the inverses corresponding to each number. Of course, 1, the inverse of 1 is 1. Multiply 1 times 1, you get 1. In the case of 2, is 7. 2 times 7 is 14, which gives what remainder divided by 13? 1. And 3 times 9, 27, again, remainder 1. For 4, it's 10. For 5, it's 8. For 6, it's 11. And so, right, for 7 is 2. If it's 2 for 7, 7 for 2. If it's 5 for 8, then 8 for 5, and so on. And of course, that goes for the corresponding negative numbers if we look at those. Okay.